HANNA, a novel hard-constraint neural network, is designed to predict activity coefficients in binary mixtures. Unlike traditional neural networks that disregard physical laws, HANNA adheres to thermodynamic consistency criteria, ensuring symmetric predictions under component permutation. By incorporating explicit physical knowledge into the network architecture, HANNA maintains consistency with the Gibbs-Duhem equation and accurately models pure components. The model leverages deep-set neural networks to achieve this, and its architecture is designed to strictly enforce physical relations and constraints. This approach addresses the limitations of traditional neural networks in chemical engineering, where sparse training data and inconsistent predictions hinder their adoption. HANNA's design overcomes these challenges by incorporating explicit physical knowledge into the network, ensuring that predictions obey physical laws and boundaries. HANNA was trained and evaluated on 317,421 data points from the Dortmund Data Bank, significantly outperforming the state-of-the-art UNIFAC model in prediction accuracy. HANNA requires only the smiles of the components as input, making it applicable to any binary mixture of interest. This approach is particularly important in chemical engineering, where thermodynamic models must yield physically consistent predictions to be accepted in practice. Physics-informed neural networks, PINNs, have been successful in various fields, but their soft-constraint approach may not always be sufficient. HANNA's hard-constraint design addresses this limitation, strictly enforcing physical relations and constraints in the network. This approach is considered challenging to develop but is essential in thermodynamics, where physically inconsistent predictions are unacceptable. HANNA's architecture and training methodology demonstrate a promising solution to the challenges faced by traditional neural networks in chemical engineering. By incorporating explicit physical knowledge and strictly enforcing physical constraints, HANNA achieves accurate and consistent predictions, making it a valuable tool for various applications in the field. HANNA, a novel hard-constraint neural network, has been developed for predicting activity coefficients in binary mixtures. This approach addresses a significant gap in the field by strictly enforcing thermodynamic consistency criteria, which previous methods were unable to achieve. The architecture of HANNA consists of four main components: pure component embeddings, refining pure component embeddings, learning mixture embeddings, and enforcing physical consistency criteria. Pre-trained Chem-BERTA2 is utilized to generate pure component embeddings from SMILES strings, which are then fine-tuned to predict thermodynamic properties. The component embedding network refines these embeddings by concatenating information on standardized temperature and composition, resulting in a lower dimensional representation tailored for thermodynamic mixture property prediction. The mixture embedding network processes the refined component embeddings, and the outputs are aggregated using a sum operation to ensure permutation invariance. The resulting mixture embedding is fed into a property prediction network, yielding a preliminary prediction of the molar Gibbs excess energy. To guarantee physical consistency, the preliminary prediction is further processed to comply with the remaining consistency criteria. The final predicted molar Gibbs excess energy is calculated using equation 5, which incorporates the cosine distance between the two component embeddings. This ensures that the predicted energy becomes zero in the case of pure components and that identical component embeddings result in a zero energy. The logarithmic activity coefficients are derived in a thermodynamically consistent manner, ensuring that HANNA's predictions fulfill the physical consistency criteria. The architecture is designed to satisfy the requirements of equations 1, 3, and 4, guaranteeing that the predicted activity coefficients are physically consistent. By learning the molar excess Gibbs energy GE of the mixture rather than the individual activity coefficients directly, HANNA ensures strict thermodynamic consistency. The values of the activity coefficients can then be obtained from GE by the laws of thermodynamics. The Gibbs-Duhem consistency of predicted activity coefficients is ensured by calculating lane gamma I through partial differentiation of the excess Gibbs energy, GE, as shown in equation 7. This approach utilizes the autodifferentiation function, autograd, from PyTorch to compute lane gamma I, thereby maintaining permutation equivariant predictions. The HANNA model is trained end-to-end on 317,421 data points for lane gamma I in 35,012 binary systems from the Dortmund Data Bank, DDB, with a random split into 80% training, 10% validation, and 10% test sets. The model's performance is evaluated on the test set, comparing it to the modified UNIFAC Dortmund model. However, it is noted that the UNIFAC training set is not disclosed, and a large share of the data considered may have been used for training UNIFAC, introducing a bias in favor of UNIFAC. The performance is compared using a system-wise error score, calculating system-specific mean absolute errors, MEA, by averaging the absolute deviations of the predicted logarithmic activity coefficients from the experimental data for each system from the test set. The results show that HANNA significantly outperforms UNIFAC, with a mean MEA reduced to almost a third of UNIFAC's, indicating a reduced number of poorly predicted data points. The median MEA is also significantly reduced, indicating higher overall accuracy. The performance of HANNA on the complete test data, including those that cannot be predicted with UNIFAC, is similar to the UNIFAC Horizon performance. The robustness of HANNA over different random seeds for data splitting is demonstrated in Figure S4 in the supporting information. Figure 2 presents a comparison of the system-specific mean absolute error, MEA, of predicted logarithmic activity coefficients, lane gamma I, between HANNA and UNIFAC models. The results are divided into two categories: the UNIFAC Horizon, where test data can also be predicted by UNIFAC, and the Complete Horizon, which includes all test data. Three scenarios arise in the test set: systems with new component combinations, systems with one unknown component, and systems with both unknown components. Although not differentiated in Figure 2, HANNA significantly outperforms UNIFAC in extrapolating to unknown components, as demonstrated in Figure S.3 of the supporting information. Figure 3 displays the results of the test set in a histogram representation of the system-specific MAE, along with the cumulative fraction of test systems that can be predicted with an MAE smaller than the indicated value. The left panel compares HANNA and UNIFAC predictions on the UNIFAC Horizon, while the right panel shows HANNA predictions for the complete test set. The results highlight HANNA's improved prediction accuracy over UNIFAC, with approximately 74% of test systems predicted with an MAE smaller than 0.1, within the range of typical experimental uncertainties, compared to 54% for UNIFAC. Figure 4 provides detailed results for 5 isothermal systems in the test set, showcasing predicted activity coefficients as a function of mixture composition, internally predicted Gibbs excess energies, and the resulting vapor-liquid phase diagrams obtained using the predicted activity coefficients. These results demonstrate HANNA's ability to accurately predict thermodynamic properties and phase behavior of binary systems. HANNA, a novel hybrid thermodynamic model, integrates the flexibility of neural networks with rigorous thermodynamics to predict activity coefficients in binary mixtures. This model ensures strict thermodynamic consistency and can generate predictions for any binary mixture whose components are represented as Smiley strains. Trained on comprehensive data from the Dortmund Data Bank, DDB, HANNA outperforms the best physical model, modified UNIFAC, Dortmund, in terms of prediction accuracy and applicability. Ablation studies highlight the importance of hard-coding physical knowledge in HANNA's architecture for both thermodynamic consistency and predictive accuracy. The approach demonstrates the power of combining the strengths of flexible neural networks with that of physical knowledge. Despite being trained on only a fraction of about 0.1% of the binary systems, HANNA generalizes well. This method could be extended to include other types of thermodynamic data, such as enthalpies of mixing, or activity coefficients determined from liquid-liquid equilibria. It could also be adapted to multi-component mixtures by using HANNA to predict the binary subsystems and employing established physical models based on pair interaction for extrapolations. Furthermore, the method could be transferred to other thermodynamic modeling approaches, e.g., equations of state based on the Helmholtz energy, and even to merge physical theory with neural networks in other scientific fields. The comparison of HANNA's predictions with experimental test data from the DDB shows excellent agreement between predicted and experimental data for various binary systems, including low boiling azeotropes, approximately ideal systems, and high boiling azeotropes. Figure 4 illustrates the Gibbs excess energies, resulting logarithmic activity coefficients, and isothermal vapor-liquid phase diagrams for 5 systems from the test set as predicted by HANNA, alongside comparison to experimental test data from the DDB. None of the depicted systems were used for training or hyperparameter optimization, further validating the model's performance. The plots show that HANNA accurately predicts the phase behavior of these binary systems, demonstrating its capability to provide reliable predictions for a wide range of systems without requiring extensive experimental data. This is significant as it indicates the potential of HANNA to streamline the development of new products and processes in various industries by providing accurate predictions of thermodynamic properties, thus reducing the need for costly and time-consuming experimental measurements. The vapor-liquid equilibrium data points were pre-processed to exclude pressures above 10 bars, and activity coefficients at infinite dilution were adopted from the Dortmund Data Bank. The VLE diagrams in Figure 4 were predicted using equation 8, with activity coefficients from HANNA and per-component vapor pressures from the DDB. The dataset comprises 317,421 data points, covering 35,012 binary systems and 2,677 individual components. Numerical embeddings of the components were generated from the pre-trained language model Chem-Berta-2, trained on a large database of smiles. The 77MMTR model generated 384-dimensional input vectors for each pure component. The dataset was split system-wise for training, validation, and testing of the hybrid model HANNA. The training set consisted of 80% of the binary systems, the validation set consisted of 10%, and the testing set consisted of the remaining 10%. HANNA was trained on one A40 GPU using the Atom optimizer with an initial learning rate of 0.0005 and a learning rate scheduler. The training was stopped if the validation loss was not improving for 30 epochs, and the model with the best validation loss was chosen. The pure component embedding network, property network, and mixture embedding network consist of 1 or 2 hidden layers, with the sigmoid linear unit function as the activation function. The hyperparameter beta in the smooth L1 loss was set to 0.25, and a batch size of 512 was used. The Atom optimizer was used to update the NN weights during training, and the validation data were used for early stopping. The optimization of hyperparameters involved tuning the parameter lambda in the Atom optimizer and the number of nodes in each network, with optimal values of lambda equals 0.000001 and 96 nodes. A final version of HANNA is provided, trained on 90% of all systems and validated on the remaining 10%. This summary covers all the major points from the 4 pages, providing a comprehensive and technically accurate overview of the field. It uses a highly technical and professional tone suitable for expert researchers and stakeholders. Here is a combined summary of pages 25 to 28 of the research paper. Machine learning has been increasingly applied to predict molecular properties and chemical reaction outcomes, leveraging molecular fingerprints as input. Combining machine learning with physical knowledge and thermodynamic modeling of fluid mixtures enables the prediction of various parameters, including Henry's law constants and liquid phase diffusion coefficients, by matrix completion methods. Graph neural networks, group contribution concepts, and natural language processing have been employed to develop interpretable molecular property models. For instance, one approach predicts limiting activity coefficients from Smiles strings using natural language processing. Physics-guided machine learning models, such as SPT and RTL, have been developed to predict thermodynamically consistent activity coefficients. The literature emphasizes the significance of molecular fingerprints, such as Smiles, in encoding molecular structures, enabling the application of machine learning algorithms to predict molecular properties and chemical reaction outcomes. The combination of machine learning with physical knowledge and group contribution concepts has been shown to improve the accuracy and interpretability of molecular property models. The authors introduce HANNA, a hard-constraint neural network designed to predict activity coefficients in a consistent manner. This model utilizes a novel architecture that integrates thermodynamic constraints into its design, allowing for more accurate predictions of the activity coefficients. 2 ablation studies are conducted to understand the importance of different parts of HANNA's architecture. The ablation studies provide insight into the significance of various components within the model, further emphasizing the importance of incorporating thermodynamic constraints for consistent predictions. The paper highlights the importance of thermodynamic constraints in predicting activity coefficients accurately, demonstrating improved performance compared to traditional models. The authors present a comparative analysis of their proposed model, HANNA, against two ablation models and the widely used method, UNIFAC, for predicting activity coefficients in mixtures using deep learning techniques. The ablation models, Ablation Model 1 and Ablation Model 2, are designed to test the necessity of interaction modeling and enforcing Gibbs-Duhem consistency in HANNA's architecture. Results indicate that interaction modeling is essential for accurate predictions, as HANNA and Ablation Model 1 show similar performance in terms of smooth L1 loss, while Ablation Model 2 shows a significant deterioration in performance. This highlights the importance of interaction modeling in achieving accurate predictions. The authors also compare the performance of HANNA and UNIFAC for predicting systems with one unknown component, demonstrating that HANNA outperforms UNIFAC in this task. This suggests that the deep learning approach can effectively extrapolate to new, unseen components, which is crucial for practical applications where not all components are known. Furthermore, the authors assess the reliability of HANNA and UNIFAC models in extrapolating to systems containing unknown components, with results indicating that HANNA significantly outperforms UNIFAC in terms of reliability. This observation is supported by the box plots in Figure S3, which show that HANNA's performance is superior to UNIFAC's for both the UNIFAC horizon and the complete horizon. The hyperparameter optimization process for developing HANNA involved varying several parameters, as detailed in Table S1, with the model with the best performance on the validation data, Model 5, being selected for use throughout the manuscript. This model achieved a lower smooth L1 loss compared to other variants, indicating its superior predictive capabilities. Overall, the findings suggest that HANNA is a more reliable choice than UNIFAC for predicting activity coefficients in systems containing unknown components, particularly given the limitations of available data and the inherent challenges in modeling systems with water and infinite dilution activity coefficients. The research paper delves into the development of HANNA, a machine learning model designed to predict thermodynamic properties in chemical engineering. A detailed analysis of various hyperparameters and their impact on validation loss is presented in Table S.1. This table highlights the influence of weight decay, lambda, in the atom optimizer and the number of nodes on the smooth L1 loss function. The study also assesses the robustness of HANNA by comparing results for different splittings of the systems from the complete dataset into training, validation, and test sets. Figure S.4 displays box plots for the system-specific mean absolute error, MAE, on the different test sets, indicated by different specified seeds, on the UNIFAC horizon. This analysis demonstrates high robustness of HANNA across various data splits. Moreover, the paper references Gemelling et al.'s Chemical Thermodynamics for Process Simulation, 2nd ed., which provides a foundation for understanding the thermodynamic properties and their importance in chemical engineering processes. This reference underscores the relevance of accurate prediction models like HANNA in enhancing process simulation and optimization. In conclusion, the paper emphasizes the significance of optimizing hyperparameters in machine learning models and demonstrates the effectiveness of HANNA in predicting thermodynamic properties. It also emphasizes the importance of robustness testing and the relevance of established thermodynamic principles in chemical engineering.